Hi all, my presentation is dedicated to the paper with the title Using the Temporal Data and Three-Dimensional Convolutions for Sign Language Alphabet Recognition. Here are the authors. So first of all, problem statement. So this work is the development and improvement of previous work done by authors in improving existing approach for Ukrainian sign language recognition. The main idea is to use, instead of a single image with a gesture, spatio-temporal frame data, which basically consists of multiple images, which are chronologically ordered one by one with a temporal data component. Another task is to use the most novel MobileNet v3 model for improving of recognition quality. Finally, adding more data augmentation techniques to make the dataset, the trained dataset, even bigger, and achieve a higher prediction quality measured with F1 score. So existing approaches are divided into two major groups. First group is more conventional computer vision approaches, such as hogs, bag of features, hyperplane separation. Another direction is convolutional neural networks, such as Kuznetsov, ShuffleNet, MobileNet, which are used for object detection and recognition nowadays. There are more advanced versions with three-dimensional convolutions allow to process not only single images, but also sequences of images, such as videos, with dynamic activities. So in the proposed approach, we improved the previous work with feeding the sequence of frames in the form of spatio-temporal frame to an improved model based on MobileNet v3. After that, we get a set of predictions for the spatio-temporal frame. We smooth them, and then we generate the final prediction. Part of the approach is one of the important parts of the approach is the spatio-temporal frame, which is which divides basically the input video into smaller subsequences. So this spatio-temporal frame has its own hyperparameters, such as size of the frame itself, like for instance, 5 frames from the original video is a single spatio-temporal frame. And another hyperparameter is the amount of overlapping images, so that when we have two subsequent spatio-temporal frames, we want a couple of images from the original video within those spatio-temporal frames to be overlapping, and we can tune this as a hyperparameter. So as a part of the approach, a special pipeline was built to tune those hyperparameters. So basically, we have a hyperparameter grid for two of those parameters, size and amount of overlapping images. Then we do hyperparameter selection. We pre-process the dataset because we need to pre-process the original video sequences into spatio-temporal frames. Then we perform model training. After that, we perform model evaluation with the predefined test set. This is important to have the test set predefined before starting of the dataset preprocessing, so that the comparison will be fair for all the models. And finally, after the evaluation, we can decide which hyperparameters show the best performance on the test dataset. One of the other improvements in the work is a bigger amount of dataset augmentation operations we included. So there are a couple of new, like salt and pepper, coarse dropout, gamma contrast, affine transformations, more blur and more embossing. You can see some of the examples on the images. So the idea is, with more data augmentation, the model will become more robust to different issues with the input images we can meet in future, and it will be more robust to changes in the images, more robust to changes in the environment and in the background. Also, the prediction smoothing technique is also part of the technology. So the idea is that since we are processing the data sequentially, we accumulate prediction values and drop out predictions which are highly distorted from most of the other predictions which are chronologically close. So the idea is to remove anomaly predictions we sometimes may get from our model. Finally, the dataset we got consists of 50,000 of original images. After augmentations, we got 5 times more of the data. We also maintained significant diversity in the data. For instance, in terms of the light conditions, we tried to make some of the data with bad light conditions, some with the mediocre, some with good light conditions, and also maintain this distribution in both test set and in the train set. We did this not only for light conditions, but also for image quality, for background, for blurriness, and so on. So experiments and results show us clearly that with the best tuned hyperparameters for spatiotemporal frame, MobileNet V3 clearly outperforms MobileNet V2, which is the previous generation model. And also with the 3-dimensional convolutions, which allows to train a model on sequences of videos or spatiotemporal frames, also gives consistent improvements. And finally, we achieved macro iPhone score 0.93, which is a score similar to other state-of-the-art solutions. So all the models work with real-time performance on NVIDIA K80 GPU. An example of the hyperparameters are shown also on this slide. So as a conclusion for the work, a novel architecture of MobileNet V3 was used as a basis for the gesture detection model. It was enhanced with 3-dimensional convolutions, which allowed as a consequence to use the presented spatiotemporal frame. Also, spatiotemporal frame has its own hyperparameters, and those hyperparameters were tuned for the best results as a part of the research. Additional data augmentation techniques were used to increase the train set and make it 5 times bigger than original. Also, some techniques were used exclusively only for the test split, which allowed us to prove the robustness of the approach on unseen before conditions in which the gesture can be shown. And finally, we got the 0.93 macro score F1 on the test set we collected, which is at 20% of the original data we had. Here's the contact info of the authors. You can also reach out via contacts from the university. That's all. Thanks for watching this presentation.